Hello everyone, my name is Shuaiyi Li. I'm a master student from Department of Automation in Shanghai Jiao Tong University. Today I'm going to share our recent work about non-blocking controller synthesis under partial observations. This work is collaborated with Professor Shuaiyi Li and my supervisor Professor Xiang Ying. Let's start from the background. Decision-making is the central problem in the field of autonomous robots and are widely used in many areas such as intelligent transportation, intelligent manufacturing, and smart buildings. Generally, the robots are required to generate a set of plans to accomplish a given complex high-level task. And when a robot is making a decision, it relies on its knowledge and observation of the system. However, there are times when the robot cannot obtain a perfect information of the system. For example, when the system scale is very big and complex, and all-inclusive information is hard to obtain, or the robot's sensing ability is limited, or for some privacy issue. In these cases, the robot can only obtain part of the system's information, but still needs to plan for the given task. And this problem has attracted an increasing attention. The task planning process can be modeled by a game between environment and controller, and the environment is trying to prevent the controller from accomplishing the task. Under this game-based setting, the partial observation makes the problem becomes very complex, so an assumption is usually made that is all the states with the same observation result have the same atomic propositions, which is the property that we care about. Here are some literature reviews. However, such an assumption can be impractical in reality. So in this work, we consider a more general case without such an assumption. For example, in this simple scenario, a robot is working in a physical system that can be discretized into a grid world, and is given a specific task with certain time and space order. For example, the physical space contains 2 coffee bars and a set of table and chair, and the robot is asked to pick up coffee at any bar and deliver it to the table. However, with partial observation ability of the environment, the robot doesn't have an accurate prior knowledge of where are the coffee bars, but only know a vague potential region. So all the grids in this region have the same observation at the beginning, but can have different properties. In this problem, the robot has to make a relatively inclusive plan and act according to each step's observation. As mentioned before, this game-based decision-making problem is hard to solve under a more general setting. So we adopt the concept of non-blocking from supervisory control of discrete event systems as winning condition. In the field of discrete event systems, given an automaton G, a prefix-closed language L is non-blocking if it can always reach a desired state in the future regardless of the current state. Here are some literature reviews. We can define our non-blocking controller based on this definition. If the finite path generated by the closed-loop system under a feedback controller is the subset of desired behavior set, then the controller is non-blocking. This means that under this controller, the system always holds the possibility to finish the given task, and this becomes a weaker winning condition. Now we will present the formal problem formulation and overview our solution. Now let's briefly discuss the task planning problem under partial observation in our work. We formulate the physical system into a non-deterministic transition system, which means that the transition result is influenced by the environment uncertainty. The task is described by linear temporal logic, which is commonly used and can expressively describe logical constraints for dynamic systems. The syntax is shown as follows. Also, we define observation function h to describe the controller's observation ability of the system. The controller is defined as a function with the input of the finite observation sequence up to now and the output of an control action. The system under the controller's operation is denoted by Tc, and we want to synthesize a controller with non-blocking property. Now let me formally describe our problem. For a given system T, the observation function H and LTL task phi, we want to synthesize a controller C such that the system's finite trace, which is the sequence of properties we are interested in, can always preserve the probability to turn into an infinite trace that satisfies the task. In this work, we consider a special type of LTL formula that can be accepted by a deterministic Boole automaton. Such an assumption is restrictive, but still expressive enough to describe many tasks. Here is an overview of our proposed controller design method. Firstly, we construct the product system and belief structure to represent the task completion, status, and the transition relation under partial observation. Then we define interconnected structure to zoom in the belief structure and construct winning region to describe the reachability relation between states. Finally, based on the structures constructed before, we determine whether a solution exists and generate the controller that generates control decision offline and update information according to online observations. Now I'll introduce the technical details of our solution. Firstly, as mentioned before, we construct the product transition system and the set of accepting states, and we extend the observation function to the product system. Then we construct the belief transition system, and it contains all the product states that the controller cannot distinguish. The transition relationship is determined by both action and observation result. Here is an example of the structure of belief transition system. Here is a product system. States marked with the same color have the same observation. X2, X5, and X6 are the accepting states. The initial states are X0 and X1, and the controller cannot distinguish them because they have the same observation. So this transfer into belief state Q0, so that's the other belief states. When the controller is making decisions, it is based on belief transition system, but its goal is to infinitely visit product systems accepting states. We compute the winner region in the belief transition system, and we first obtain a rough result called preliminary winning region. This can be computed using winning region computation in standard Boole game solution. In this example, preliminary winning region contains all the belief states. This means that all the belief states can infinitely visit belief states containing accepting states. But this is not enough. In this example, the preliminary winning region still contains a loop of Q0, Q1, and Q3 that corresponds to a path of X1, X3, X7 in the product system. This path goes through none of the accepting states, and this is because the construction of belief transition system omit the transition information between states. So, we construct the interconnected transition system to complete this part of information and become a zoom-in version of the belief transition system. The states and transition relationships in interconnected transition system contains both product states and the corresponding belief states. And we also define accepting states in interconnected transition systems. Then we can further prune the preliminary winning region to obtain a more accurate result. We first define the Boole winning region operators that compute the region of states that can infinitely visit a given set of states. Then we iteratively shrink the preliminary winning region on 0. We compute the states in the interconnected transition system that cannot infinitely visit accepting states inside, and we delete the corresponding belief states denoted by Ri unqualified in step I. We also delete belief states that the controller cannot avoid from reaching Ri unqualified, denoted by Ri remove. When this process reaches a convergence, we will get the final winning region of belief states. And we can prove in proposition 1 that if a controller visits states outside this region, then it cannot guarantee the accomplishment of task. In this example, we can construct the interconnected transition system on the left, and we compute the states that cannot infinitely visit accepting states and delete the corresponding belief state. Then the remaining region reaches convergence, which is the final winning region. Based on the above winning region, we can design our controller. The idea is to focus on only one initial state in the belief state towards accepting states at each time, until all the paths have reached accepting states. For example, we want x0 and x1 all visit accepting states. If we focus on x1, then we will take action a2 to make sure x1 reaches accepting states, and at the same time x0 reaches x4. So we will then take set of actions to reach accepting state x6. Until then, we have ensured both x0 and x1 have visited accepting states, and we will start and repeat this. During this process, we need to recall the history information, so we define augmented state for this purpose. Also, we need to determine which state we are currently focusing on, so we define action generation state. Combine these elements, we can design a control strategy structure. Firstly, we need to determine whether a control strategy exists. Then we alternately generate control decision offline using the above information and apply control decision online to update information according to new observation. Our detailed algorithms are as follows. Algorithm 2 is the offline decision generation algorithm, and algorithm 1 is the online control and information update algorithm. We design a rule to correctly update the augmented states and action generation states. We present a delivery scenario for illustration purpose, and also provides a simplified real-world experiment. In the delivery scenario, the robot moves in a grid world. The blue circle represents the charging station, and the red and green regions are the potential pickup and deliver destination that are picked by environment in each turn randomly. Black regions are the dangerous region. There is also a moving obstacle in the environment. It usually stays at the region of black circle but can navigate a cruise at any time. The trajectory is shown in dashed line. The robot's mission is to infinitely visit charging station, pick up and deliver the cargo. The system state contains the robot's location XA and the environment state XE, which contains the pickup location, the deliver destination location, and the moving obstacles location. The robot can move in 4 directions and can observe if the cargo is picked up or taken away, and also can detect the moving obstacle when it is nearby. The result strategy is shown in the right figure. We also done a real-world experiment that only involves random task assignment and moving obstacle avoidance. One robot is controlled by algorithm while the other acts as an obstacle and moves according to the dashed line cruise. A short conclusion. We adopt non-blockiness as a matrix to evaluate the winning condition, and we formulate and solve the non-blocking control synthesis problem for a special type of LTL tasks without assuming the relationship between observations and properties. And we provide a solution structure with offline winning region construction and online control. In the future, we plan to investigate the sure winning control problem under this setting and extend to general LTL tasks and active sensing problem. That's all for our talk, and thanks for your time and listening.